Hi, I am Sanjay Patel. In this video, we are going to discuss a necessary condition for convergence of series. So let us begin with this result. So it's a theorem. If sigma an is convergent, if sigma an is convergent series, then limit n tends to infinity, an is equal to 0. That is, the limit of the nth term of the sequence an associated with this is always 0. Remember, this condition is a necessary condition. Okay, let us prove this. So what is given here is this series sigma an. You know the meaning of this symbol sigma an, that is sigma n is equal to 1 to infinity an, and that means a1 plus a2 plus a3 and so on. So this is the given series, and we know that it is convergent, that is given. And what is the meaning of convergent series? A series is said to be convergent if the limit of its partial sums exist. And what is the partial sum? We have already defined partial sum as, we know that the partial sum is given by Sn, and that is nothing but the sum of the first n terms of the given series. So it is Sn is equal to a1 plus a2 plus a3 up to an. Okay. Now from this I can write Sn minus 1 also by putting n equal to n minus 1, or other words, the sum of the first n minus 1 terms of this series. Okay, and now if I take a difference of these two, then we get Sn minus 1 is equal to an. All these terms will be cancelled, only the term an will be left. This will be left because this is sum of a1, a2, a3 up to an minus 1 and an. So that will be cancelled. So Sn minus 1 is the nth term of the sequence an. And that we are finding because we want to find limit of an, and to prove it is 0. Okay. Now here sigma an is convergent. Now sigma an is convergent series, and therefore by definition limit n tends to infinity of Sn, that is the partial sum Sn, this sequence has a limit, and say it is equal to S. This limit exists. This limit exists. Okay, and if limit n times infinity Sn exists, then with the help of this we can find the limit of an also. So therefore I can write limit n tends to infinity an. Now I want to find the limit of an, but an I can replace by that expression Sn minus 1. So this is equal to Sn minus 1. Now since limit of this Sn exists, this limit exists, we can write this as limit n tends to infinity Sn and limit n tends to infinity Sn minus 1. And remember that as n tends to infinity, n minus 1 also tends to infinity, and both these things are same. And limit of this is S, and the limit of this is also S, because as n tends to infinity, it is obvious that n minus 1 also tends to infinity. So this is equal to 0. So what is proved? Therefore, limit as n tends to infinity, an is equal to 0 is proved. So the theorem is over. Hence the theorem is proved. Okay. Hence the theorem is proved. Just important thing about this theorem is that this condition in the theorem is only necessary but not sufficient. So we want to write some comments about this. So let me write down as the first remark, say number 1, the the condition in the above theorem is only necessary. The condition in the theorem, in the above theorem, is necessary, okay, but not sufficient. But not sufficient. That is, in other words, you can say, or you can say that the converse of this theorem is not true. The converse of this theorem, of this above theorem, is not true. Is not true. What is the meaning of this? The theorem says if sigma an is convergent, then limit of the nth term of this an is 0. Converse is not true means if limit of an is 0, then we cannot conclude that sigma an is convergent. Okay, so let us write down that is if limit n tends to infinity an is equal to 0, then sigma an, this series, need not be convergent. Need not be convergent. And whenever something is not true, we always provide some counter example in mathematics to explain that thing. So here also, I will be taking one example to explain that for a given series sigma n, we can have limit n tends to infinity n equal to 0, but the series need not be convergent. So consider the series. This is also a very, very important example. Consider the series sigma 1 upon n. Sigma 1 upon n, n is equal to 1 to infinity. What is this series? You know, it is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on. So here, for this series, the nth term is 1 upon n. So let me write down that thing. Here an is equal to 1 upon n. And therefore, it is clear that limit n tends to infinity, an, that is limit n tends to infinity of 1 upon n, and that is, we know, it is 0. Okay. So we have proved that limit of an is 0. Now I will show that this series sigma 1 upon n is not convergent, and that proves that even though limit of an is 0, the sigma an can be divergent also, or not convergent. So to prove that, let us consider this way. Now consider the series sigma n is equal to 1 to infinity 1 upon n. This we can write as 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5. Let us write some more terms to get some good idea. 1 by 8 and so on, up to infinite terms. Remember, the meaning of convergent series in simple language is if this sum is possible, if you can add all the terms and get some real number or a finite number, then the series is said to be convergent. So if the sum is possible, we call it a convergent series, and if it is not possible or if it does not exist, then it is called divergent series. So in a simple language, we can say like this. Okay. Now, what I want to do here is I want to make different groups of the terms, keeping one first and second term as it is. I am going to take these two terms, 1 by 3 and 1 by 4. Then I will take these 4 terms. Okay. So first I am taking these 2 terms, then 4 terms. Then next I will take, say, 16 terms. So here 2 terms are there, then 4 terms, then say 8 terms, sorry, not 16. Okay. And this I want to write like this: 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. Okay. What will be the next bracket? In the next bracket, the first number is 1 upon 9, then 1 upon 10, and then it will go up to 1 upon 16. So this way you can continue and write this up to infinite terms. And there are so many, there are infinite number of terms, so we can continue like this. Okay. Now the main trick here is that we'll show that this sum is greater than some other sum which is actually does not exist, or it is infinity. So how to prove that? So note in each bracket, first of all consider this bracket. In this bracket we have two numbers, 1 by 3 and 1 by 4. What I want to do is I want to replace these numbers by the, say, smallest number. Among 1 by 3 and 1 by 4, 1 by 4 is, say, smallest. As the denominator is more, the value of the fraction is less. So if I replace 1 by 3 by 1 by 4, then this sum is obviously greater than that new sum. So can I write like this? Just understand. So first two terms I am writing as it is, but here in this first bracket I am replacing 1 by 3 by 1 by 4. So what I am getting is 1 by 4 plus 1 by 4. All numbers I am replacing by 1 by 4. And it is very easy to understand. As you know, 1 by 3, okay, is greater than 1 by 4. So I can say 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. It's like that, adding 1 by 4 both the sides. So we get this thing. Just a simple explanation. Now, same way, if I replace in this second bracket all the terms by the smallest one. Which is the smallest term here? It is 1 upon 8. 1 upon 8 is the smallest value because the denominator is the highest. So this sum is greater than if I replace all the terms or all the numbers in this bracket by 1 by 8. So I can write this as 1 by 8 plus 1 by 8 plus 1 by 8, and it is 4 times, correct? And remember this greater than sign is there. So this sum is strictly greater than this sum. And we are adding all such sums. Same way, what you will get here is replacing in the third bracket all numbers by the smallest number, that is 1 by 16. So we'll get 1 by 16 plus 1 by 16 and so on. And that is also how many times? It is 8 times. So there are 8 terms here. So plus and so on and up to infinity. Now let us simplify this last step. So what we get here is this is equal to 1 plus 1 by 2 plus 1 by 4 plus 1 by 4 is 2 times 1 by 4. So that is 1 by 2. Again 1 by 8 plus 1 by 8 plus 1 by 8 4 times. This is 4 times. So 4 times 1 by 8 is again 1 by 2. This is 8 times 1 by 16. So it is also 1 by 2. So likewise, if you correct the terms in this order, what you can prove is all the sums of these brackets are 1 by 2, and this will go up to infinite number of terms. Okay. So this says that this sum, okay, this if you add 1 by 2 to 1 by 2 plus 1 by 2, you will get 1. 1 by 2 plus 1 by 2, you will get 1. So 1 plus 1 plus 1 plus 1, infinity times. So this tends to infinity. Okay. So what I have proved is this left hand side sum sigma 1 upon n, this sum is greater than this sum, and this sum is going to infinity. This sum does not exist. So therefore I can say that this sum sigma 1 upon n is also infinity, and in other words this sigma 1 upon n is not convergent, or it is divergent series. Okay. So it is not convergent. So this is number 2. From 1 and 2, we can say the converse of the above theorem is not true. So from 1 and 2, the converse of the theorem is not true. Okay, is not true. So this is my first remark, in which we have discussed that this condition in the theorem, the main theorem is if sigma an is convergent, then limit of an is 0. The converse is not true. This condition is only necessary but not sufficient. Let me show you here. If sigma n is convergent, then limit n tends to infinity, n is equal to 0. It means if a series is convergent, it is necessary that the nth term must go to 0 as n tends to infinity. But the converse is not true. So given a series sigma n, if limit of n is 0, we cannot conclude that the series will be convergent. Okay, but the use of this result is in order to prove a given series is divergent, and that I will show you how. That is very, very interesting and based on simple mathematical logic. So what I am going to do is, let us write down the second remark, second note. What we have proved here is, we have proved that sigma n is convergent. Okay, that implies limit of an as n tends to infinity is 0. So we can call this statement as P and another statement as Q. So we have P implies Q is true. Let me write this way. This is my statement P and this is my statement Q. And we know that if P implies Q is true, then it is equivalent to say that not Q implies not P. This is a contrapositive. So what we can say, if not Q means if this statement is not true, that is I can write. So therefore, if I am writing not Q implies not P, because this is P implies Q and the not Q implies not P is this limit n tends to infinity, n is not 0, this limit is not 0, then this is not true. Sigma n is convergent, that statement is not true means sigma n is divergent. Sigma n is divergent. So this is very, very useful and important thing about this theorem. It gives us a rule of proving a given series is divergent. Okay, so just remember this. Whenever you want to prove a series is divergent, just find the limit of nth term, and if it turns out to be not equal to 0, then you can immediately say the series is divergent, means not convergent. But if it is 0, we cannot say anything. So this is very, very important. We'll discuss some problems based on this, and that will clear your this idea. So let me take some examples. Say examples. Just remember that using this result, you can prove only divergence of a given series, not convergence. So first problem we want to discuss here is this. Say, I will just write the common thing. Discuss convergence of the following series. The following series. So I'm taking the first example. So it is sigma cos 1 upon n. Consider this series. For this series, we can say that the nth term an is cos 1 upon n here. And if you take the limit of this nth term, that is n tends to infinity n, that is limit n tends to infinity of cos of 1 upon n. And that is nothing but cos 0. As n tends to infinity, 1 upon n tends to 0, and cos 0 is 1. So what we have proved is limit of the nth term an as n tends to infinity is 1, which is not equal to 0. So if limit of the nth term is not 0, we can conclude that the given series, that is sigma cos 1 upon n, is not convergent, or it is divergent series. Okay, so this is a simple example. Let us take another interesting problem. Suppose if I take the second problem, sigma, say 2 plus 3 upon 3n upon say 3 minus 2n. So here in this case, we have sigma an, that is sigma 2 plus 3n upon 3 minus 2n. So I can say what is an? An is 2 plus 3n upon 3 minus 2n. So now if you find the limit of this nth term, and you know very well how to find limit of sequences that you must have studied in your schools. So for finding limit as n tends to infinity of such an expression or such a sequence, what we do is we divide by the highest power of n in the numerator and denominator when we have polynomial kind of expressions in numerator and denominator. This is a linear polynomial. So I will divide by the degree n raised to 1. So what I will get is 2 by n plus 3. Divide numerator and denominator each term by n, and that will not make anything new. So 3 by n minus 2. As a result, we can write down the limit of this as n tends to infinity. This goes to 0 and 3 is constant, remains as it is. And this also goes to 0 as n tends to infinity. So 3 upon n tends to 0 and this is equal to 2 as it is. So final answer is minus 3 by 2. And it is not equal to 0. So what is the conclusion? Therefore we can say sigma an, that is 2 plus 3n upon 3 minus 2n is not convergent, or it is divergent. Okay. So whenever we have polynomial kind of expressions in numerator and denominator, we can use this technique. Another example, say sigma n square plus 1 upon say 2n square plus 3. Okay, let us solve this. So here again you note that an, that is this is the nth term, that is n square plus 1 upon 2n square plus 3. So therefore if I find the limit of this an as n tends to infinity, then it gives me limit n tends to infinity of this rational expression type of thing, 2n square plus 3. So this limit now we can find, as I told you, when we have polynomials, we choose the highest degree, and here the highest degree is 2. So we divide every term in the numerator and denominator by n square. So what we get here is limit n tends to infinity, 1 n square by n square is 1 plus 1 upon n square upon 2n square by n square is 2 plus 3 upon n square. And as n tends to infinity, 1 upon n square tends to 0. So 1 plus 0 upon this 3 upon n square also tends to 0. So this is 2 plus 0. Just keep in mind this very important limit n tends to infinity, 1 upon n raised to k is equal to 0 if k is positive. Okay. So this is equal to 1 by 2. This is equal to 1 by 2. And it is not equal to 0. So the conclusion is the given series sigma n square plus 1 upon 2n square plus 3 is not convergent. In other words, it is divergent. Okay. Let us take one more problem. So number 4. Consider the series sigma, say 1 plus 3 upon n raised to n. Okay. So here in this we have the nth term an is equal to 1 plus 3 upon n raised to n. So limit of this as n tends to infinity, limit n tends to infinity an is equal to limit n tends to infinity of 1 plus 3 by n whole raised to n. You know how to find limit of this. For that, we are going to use the famous result about limit of the sequence 1 plus 1 upon n raised to n. You know this thing, limit n tends to infinity 1 plus 1 upon n raised to n is equal to e. Okay. We can use this if we have something like that 1 plus whatever it is here, its reciprocal should be there in the power. So it is 1 upon n and the reciprocal of 1 upon n is n. What do we have? In this case, it is 3 upon n. So I should have say n by 3 here, but there is no 3. So I will try to bring 3 in the power of that 1 plus 3 by n in this manner. using some simple mathematics. 3 by n raised to n by 3. I want the reciprocal of this. And this whole raised to, we can write, because we have to maintain the same thing, raised to 3. So this 3 gets cancelled and you will get the same thing. Okay. Now you can find the limit of this. So as n tends to infinity, okay, this thing tends to e. So because of this formula, so this is e raised to 3 finally. Okay, and e raised to 3 is not equal to 0 because e is the t rational number 2.718 and so on. And therefore, the conclusion is the series sigma 1 plus 3 by n raised to n is not convergent. Is not convergent. Okay. Let us finally take one more example of a different type. Say, consider number 5. Discuss the convergence of this series a upon b plus a plus x upon b plus x plus a plus 2 into x upon b plus 2 into x and so on, like this. So you can understand the pattern here, okay, up to infinite terms. Here x is a non-zero real number. If it is 0, then also we can prove that this series is not convergent. So let us discuss the convergence of this series. So here the given series sigma an, we want to write the nth term here. So you observe this is a upon b, then a upon b plus x here, then plus 2x plus 3x. So for the first term we have, there is no x, so it is 0x you can say, then 1x, then 2x for the third term. So in general we can write the numerator as a plus n minus 1 into x, where n is equal to 1 to infinity, and it's the same way we can write for the denominator b plus n minus 1 times x. We can verify for n equal to 1, this is 0, so we'll get only a upon b first term. For n is equal to 2, we'll get a plus x, 2 minus 1 is 1, and b plus x. So therefore we have an is equal to a plus n minus 1 into x upon b plus n minus 1 into x. Again, it's a polynomial kind of expressions in numerator and denominator. So limit of this an as n tends to infinity is limit n tends to infinity of a plus n minus 1 into x upon b plus n minus 1 into x. So here also I multiply and divide, here I divide every term in the numerator and denominator by say n minus 1. So what I will get is a upon n minus 1 plus x divided by b upon n minus 1 plus x. Okay, and if you take the limit of this as n tends to infinity, n minus 1 also tends to infinity, and a and b are fixed numbers. So this a upon n minus 1 tends to 0 and b upon n minus 1 also tends to 0. So what we are left with is 0 plus x, and here also 0 plus x. This n times infinity does not affect x, where x is a fixed non-zero real number. So what we get is x upon x, and since x is not 0, this is equal to 1. Okay, so what I have proved is the limit of an is 1, and therefore we can say that this limit is not 0. This limit is not 0. So what I have proved is limit n tends to infinity, an is not equal to 0, and hence the given series sigma an is divergent. Okay, so we have discussed an important necessary condition for convergence of series. If sigma an is convergent, then remember that limit n tends to infinity an is equal to 0, but the converse is not true. That is, if limit n tends to infinity n is 0, then we cannot say that sigma n is convergent always. And but it is very useful to prove a given series is divergent if you can find limit of an and if it is not equal to 0. Okay, so in the next lecture we are going to discuss some properties of convergence series. That suppose if you have two series, then what can you say about their sum, and if you multiply by something, what happens? Okay, and some interesting results which are useful later on. So thank you.